Hello, Assalamualaikum. This video will show you step by step on how to solve Bernoulli equations problems. So for this example, the figure here is exactly the same figure that I showed you in the previous video part 4, where the large water tank and the water that flowing out from the tank. So the question says that a large tank open to atmosphere is filled with water to a height of 5 meters from the outlet tap. A tap or the outlet hose near the bottom of the tank is now opened and water flows out from the smooth and rounded outlet. Determine the water velocity at the outlet. So you have to be very careful. Point number 1 is at the surface of water in the tank. Point number 2 is, where is point number 2? Is at the outlet. Okay, let's do this together. Firstly, you have to give assumption. This assumption is important. There are usually a few assumptions that are very important to ensure that we can use Bernoulli equation. First of all, we have to assume that water in the tank and flowing out at the tap outlet is steady flow. Why we say it's steady flow? Because at point number 1, at the surface of the water in the tank is decreasing slowly but steadily, similar to velocity of water that running out from the outlet. Although the water running out or flowing out at certain velocity, but it is in steady condition. Point number 2, the water in both tank and the outlets are in compressible flow. Third assumption that should be included in this problem is also the water flow in the tank and also at the outlets are frictionless. Though it's not really frictionless, but we have to give this assumption, otherwise Bernoulli equations are not valid. Alright, after having these assumptions, then we can write down the Bernoulli equation. So remember, when we do have 2 points, that means we have to have Bernoulli equation at point 1 and Bernoulli equation at point 2. So we write it down. Bernoulli equation P1 over rho G
over 2G plus Z1 equal to P2 over rho G plus Z2 power over 2G plus Z2.
Alright, then as I mentioned in the previous video, we have to do some simplification so that the equation that we have is mathematically can be calculated, and to avoid any unnecessary information. Okay, firstly, to simplify this equation, we have to go variable by variable. Let's look at variable number 1, which is pressure, P. So when doing that, we have to look at both sides, P, pressure number 1 and pressure number 2. So pressure at point 1 and pressure at point 2, we have to look at both of them. Pressure 2 at the outlets, pressure at point 1 at the surface of the water in the tank is, yes, we have to look at the question text. They said a large tank open to the atmosphere. That means the air and even the water at point 1 is actually exposed or open to atmosphere. So P1 is P atmosphere. How about pressure at point 2? Pressure at point 2 is at the outlet. So pressure at the outlet definitely exposed to atmosphere. So P2 is also P atmosphere. So definitely rho also similar because both of them are water, and then gravity and gravity. So mathematically when you move the P2 to the left side, then both of them will give you 0. So velocity at point 1, this is a bit tricky. Then I think you have to always bear in mind whenever they say in the question and in the figure, they said large or tank, and then the point, and then the location in the tank is at the surface of the water. We have to consider the size of the tank. What I mean by that is, when you look at the point 1, what is the velocity that may be occur at the point number 1? The velocity that might be happen at point number 1 is actually the rate of the water that decreasing over time, right? So whenever 5 become 4.9, become 4.8, so basically it's actually the velocity that involved. However, because of the size of the tank is large, this flow rates of flow rates of the water decreasing very slow, and it's considered almost 0 meter per second. So for V1, we have to give assumption like this: the size of the tank is large relative to what? The outlet or the outlet tap. Because of the size of the tank is large enough relative to the outlet tap, the velocity of water at the outlet tap is maybe high, but the velocity of the water at the surface, specifically at point 1, is very low. So take them out as well. How about V2? Velocity at point 2 definitely must have a specific number because the water running out from the tap outlet. Okay, so we maintain the V2. How about Z1 and Z2? Z1 and Z2 represents the position, the elevation or the vertical position from the reference point. So Z1 and Z2 represents the position at point 1, position at point 2. So when you want to analyze where is Z1, where is Z2, you have to look at the figure. When you look at the figure, you will see usually they have to say that where is the position of 0 meter high. So 0 meter high is actually
represented by point 2. Alright, and from point number 2, it goes up to point number 1 with 5 meter. So basically, this is where the position of Z2, this is where the position of Z1.
So after we know that Z2 is equal to 0 meter position, Z1 is equal to 5 meter position, so Z2, we can take Z2 out because Z2 is equal to 0, but Z1 we maintain. Alright, so after having this simplification, what left to us is only this: Z1 equal to V2 power of 2 over 2G. Then because the question asks us determine the water velocity at the outlet, so
V2 power of 2 over Z1 times 2G, and then you move the square to become square root, then it becomes Z1 times 2G.
Just insert the numbers here.
V2 equal to Z1 is equal to 5 meter, right? 2 times 9.81 for the gravity, and then you square root, you get something over something meter per second. Alright, that's example number 1.
Look at the example number 2. In the example number 2 here, we have a water conduct from, let's say, point 1 to point 2. Water travel, so it's water. Okay, what is the rho for water, density for water? Rho equal to, let's say, 1000, generally 1000 kilogram meter at 20 degrees C temperature. So water travel inside a lower pipe, average with average velocity 3.5 meter per second. Why they said average velocity? Maybe some of you will ask me why average velocity, because if you remember, we talked about this in the chapter 1 and even in the introduction. When the water moves, let's say, in a pipe, the water velocity always occur like this for the uniform flow, steady flow. At this position,
it must be, let's say this one 5 meter per second. At this position, maybe 3.5 meter per second. Maybe this one also 3.5 meter per second. So basically, because of the uniform flow, it's in parabolic. So maximum velocity will be somewhere here. Max. Let's say average velocity. So it's something like this. It's something like we have to give assumption that from this point to this point, from this point to this point, we consider, let's say here is minimum velocity, maximum velocity, and then this minimum velocity. So the average is basically mean plus max, and then you divide it by 2. So you get the average velocity, overall velocity. Because whenever you put it down, all of them together, you still have parabolic flow, but the velocity here is the velocity average.
okay, that's velocity average. So let's go back to the question. The diameter of the pipe, which pipe? Lower pipe. So the diameter is 0.1 is 6 centimeter. Then the water continuously flow into a smaller pipe at the higher section of 3.5 centimeter diameter. So how about the velocity too? It doesn't mention. Diameter of H height. So this is H. So basically H here represents Z2. This is Z1, represents the position of 0.1. So definitely Z1 equal to 0 meter. Z2 equal to H. And then the pressure at the lower pipe section is 100 kPa, kilopascal, more than the pressure at the upper pipe section. What it means by more, it simply said that it's plus pressure at point 2. Now we have to write down the Bernoulli equation quickly. Sorry, Z1 equal to, we do have, in this question we do have V1, right? Definitely rho and G we do have it. 2G we also have it. Z1 equal to 0, we have it. P2 we don't know. V2 also we don't know. Z2 equal to H. Z1 equal to 0, right? So P1 equal to 100 kPa plus P2. Do we have enough information here? So P1 is equal to 100. When you look at kilopascal, remember kilopascal, the SI unit for kilopascal is pascal. So the original unit. So you have to change from 100 kilopascal to 100,000 pascal. Okay?
Over, sorry, this one plus P2, because they say 100,000 pascal, plus P2, rho G plus V1 is 3.5. Okay? V1 power of 2 over 2G. Z1 already 0 equal to P2 over rho G. Okay? Plus V2, we don't know V2, power of 2 over 2G plus Z2 equal to H. Alright, there are
several variables here that we cannot solve it without knowing. This one we have the number, but this one we don't know, right? How can we calculate the H if we do have 3 variables in this question? So firstly, we have to know what is V2. How can we know that? Alright, this is a good question. So remember, in the continuity equation, we believe that for the steady incompressible flow a pipe conduct, the mass balance at point 1 here and point 2 here is equal. So basically you can write down continuity m.1 equal to m.2. Remember, m dot equal to rho times
equal to rho V2 times area, cross-sectional area at point 2. Rho definitely is same, right? Because it's water. So both of them have similar density. Just take them out. So you get V1 A1 equal to V2 times A2.
Having this, definitely we can calculate velocity 2 because we have the value for area, we have the value for velocity 1. So you just bring in inside V2 is equal to 3.5 meter per second times area 1. Area 1, what is the diameter for area 1? So area for the pipe, cylinder pipe, always pi d power of 2 over 4. Remember that. 6 centimeter. Careful, it gives us in centimeter. You have to change it to meter so that it's in SI unit. So it becomes 0.06 meter. So basically, velocity at point 2 is equal to velocity at point 1 times area, cross-sectional area at point 1 divided by cross-sectional area at point 2. So you write down everything.
Velocity 1 is 3.5 meter per second times area, cross-sectional area at point 1 is pi times area 1, 6 meter. So, 6 centimeter, then you change to SI unit 0.06 meter power of 2, right? Divided by 4 over area at cross-sectional 2, pi times cross-sectional 3.5 centimeter. Again, careful, change it to SI unit to become 0.035 meter. So 0.035 power of 2 over 4. Then you get the value of V2 meter per second.
Now having this, definitely it will make our job easier. So we can fill in the velocity 2 here in this one. Okay, we don't have enough space here, so I bring this part to here. Okay, then we can simply write down again 100,000 Pascal plus rho g plus the V2 that we just got. What is the V2? I calculated V2 equal to 10.28 meter per second. You may double check my calculations here. So velocity at point 2 as 10.28 divided by 2g plus h.
So mathematically, do the mathematics. So you put the same variable together, 100,000 Pascal plus P2. You move this one to here, minus P2 over rho g. Rho, the density of the water, as I said earlier, 1000 times 9.81 plus this one to here, velocity with velocity 3.5 minus 10.28 over 2 times 9.81 divided, equal to h. Then
we get the h. So h become 10.193 from here, from this, plus minus 0.346. So h become 193. So 9.84 meter. Okay, so the h of 9.84 meter is actually the Z2. Okay, I probably might do the wrong calculation here, but you can recalculate to get the exact answer of the h. Yep. So remember, in this question they require us to go back to continuity equation so that we can fill in variables, unknown variable in the Bernoulli equation. Then you can solve the Bernoulli equation to get the h. Alright, so these two examples are kind of like familiar or common question in Bernoulli equation. I'll see you again in the next video.